Picture this, a traveler older than mountains, colder than the void between galaxies, hurtling through our solar system at 137,000 miles per hour. For billions of years, it has known only darkness and silence. And then, on October 29th, 2025, as it swung past our sun at the closest point of its brief visit, something impossible happened. It turned blue. Not the pale blue of distant ice, not the faint blue tint of reflected starlight, but a blue so vivid, so impossibly bright, that it outshone the sun itself in certain wavelengths. A blue that, according to the basic physics we've trusted since the 19th century, simply cannot exist in an object 10 times cooler than our star's surface. This is 3I Atlas, the third interstellar visitor ever confirmed in human history. And in the 72 hours since it emerged from behind the sun, every piece of data we've received has made the mystery deeper. Because here's what we know. This object is accelerating in ways gravity alone cannot explain. It's emitting 4 grams of nickel every second, an industrial compound that shouldn't exist in nature at these concentrations. It appeared from the exact region of sky where 48 years ago we received the most powerful unexplained radio signal in history. And now, during its closest approach to our star hidden from Earth's telescopes behind 93 million miles of solar fire, it changed color in a way that rewrites what we thought we understood about matter light and the cold mathematics of interstellar space. 9 separate anomalies, each one unlikely, together forming a pattern with odds of 1 in 10 quadrillion. Tonight, we're going to walk through what happened. We're going to sit with the questions that keep astronomers awake and draw the rest of us into contemplative wonder. We're going to explore what it means when the universe sends us something we cannot fully explain, and what that visitor might be trying to tell us, if anything at all. This isn't about aliens or conspiracy. This is about a moment in cosmic time when human beings, armed with the finest instruments we've ever built, watched something ancient and unknowable pass through our small corner of space, and realized we might be seeing either the rarest natural phenomenon ever recorded or the first confirmed evidence that we are not alone. By the end of this journey, you won't have answers. Neither do I, neither does anyone, but you'll understand why this matters. Why scientists are arguing, why governments are watching, and why on December 19th, when 3I Atlas makes its closest approach to Earth, the entire world will be holding its breath. Let's begin where all good mysteries begin, with light and what it remembers. There is something almost sacred about watching an object die in light. 3I Atlas began its journey long before humans existed. The mathematics suggest it's between 3 and 11 billion years old, potentially twice the age of Earth, older than most stars currently burning in our night sky. It formed in a cloud of gas and dust, orbiting some distant, unknown star. Perhaps that star still exists, a faint point of light we've catalogued but never named. Perhaps it went supernova eons ago, scattering its children across the galaxy like seeds in a cosmic wind. This comet, or whatever it truly is, has been wandering the Milky Way's interstellar depths for so long that our entire solar system has circled the galactic center multiple times since its birth. It has passed through regions of space we will never visit. It has witnessed stellar nurseries being born and dying. It has been bathed in the radiation of countless supernovae, frozen in molecular clouds so cold that chemistry itself nearly stops, and warmed briefly by the distant glow of galaxies colliding millions of light years away. And then, by pure chance, or perhaps not chance at all, its trajectory intersected ours. Interstellar space is not truly empty. It's filled with thin hydrogen trace elements, cosmic rays, ancient photons from the Big Bang. But to any object traveling through it, the experience is one of profound isolation. The nearest star to any given point in the galaxy is typically several light years away. At 3I Atlas's velocity of 68 kilometers per second, fast by human standards, crossing even 1 light year takes more than 4,000 years. Imagine that journey. not as a spacecraft with sensors and purpose, but as a frozen lump of ice rock and mysterious chemistry drifting in darkness so complete that the entire sky barely provides enough light to cast a shadow. For millions, perhaps billions of years, 3I Atlas knew only cold and void, until July 2025 when something changed. As the comet crossed into the outer regions of our solar system still beyond Neptune's orbit, the sun's photons began to reach it in meaningful numbers for the first time in eons. Not enough to warm it significantly, not yet, but enough to trigger the first stirrings of activity. Volatile ices preserved in near absolute zero cold for geological epochs began to sublimate. Molecules that had been locked in crystal lattices since before Earth's oceans formed started to break free, streaming away into space. By the time astronomers discovered it on July 1st, 3I Atlas was already active, already showing the faint glow of a coma, the cloud of gas and dust that surrounds an awakening comet. But here's where the sacred geometry begins to emerge. The object's trajectory brought it almost perfectly aligned with the plane where Earth and the other planets orbit the Sun, a flat disk called the ecliptic. Most objects in interstellar space move in random directions. The chance that one would naturally align so precisely with our planetary system is roughly 1 in 500. It's as if 3I Atlas had chosen to meet us on our own terms, to pass through our world rather than merely near it. As 3I Atlas approached the Sun through September and October, astronomers watched it closely. The James Webb Space Telescope observed it. Hubble captured images showing a teardrop-shaped coma of dust streaming behind it. Ground-based observatories in chilly Hawaii and across the world tracked its motion, measured its brightness, analyzed the light it reflected. The early observations showed exactly what you'd expect from a comet, a reddish hue from dust particles scattering sunlight. This is basic physics. Dust grains preferentially scatter longer wavelengths just as Earth's atmosphere turns sunsets red. Every comet we've ever studied, hundreds of them, shows this characteristic color when warmed by solar radiation. Then came October 29th, perihelion, the closest point to the Sun, where 3I Atlas reached a distance of just 1.36 astronomical units, about 126 million miles, roughly between Earth's and Mars's orbits. At this moment, hidden from Earth's view behind the Sun itself, something profound occurred. When the object emerged into the view of spacecraft coronagraphs, instruments designed to block the Sun's overwhelming glare and study its corona, multiple independent observers, using different technologies, all recorded the same impossible thing. 3I Atlas had turned blue. Not slightly blue, not tinged with blue, bluer than the Sun itself. Let me help you understand why this matters. The color of any glowing object is determined by its temperature and the specific processes generating light. The Sun's surface sits at 5,800 degrees Kelvin, which produces its characteristic yellow-white glow. Hotter objects emit bluer light. Cooler objects emit redder light. This is the Stefan Boltzmann law, confirmed by more than a century of physics and every observation we've ever made of stars, planets, and comets. Even at its closest approach to the Sun, 3I Atlas should be roughly 10 times cooler than the solar photosphere. A cold object cannot naturally emit bluer light than a hot one through thermal radiation alone. And yet there it was. Blue. Impossibly, undeniably blue. Blue is not just a color. It is a story that molecules tell about their recent past. When certain molecules are excited by ultraviolet radiation from the Sun, they can emit light at specific blue wavelengths. Carbon compounds, cyanogen radicals, diatomic carbon glow blue when sufficiently energized. This happens in comets. We've seen it before. But the intensity of the blue glow from 3I Atlas was extraordinary. To overpower the reflected red light from its dust to shine blue enough to appear brighter than the Sun in those wavelengths would require an enormous rate of gas emission, far more than any comet has ever produced at this distance from our star. The amount of outgassing needed to create this blue coloration should have torn the object apart. We should have seen fragmentation, multiple bright points, as pieces broke away, a debris field spreading through space. Instead, the nucleus remained coherent, structurally intact, holding together even as it supposedly vaporized enough material to create this impossible glow. Think about what this means in human terms. When we witness something that defies the rules we thought governed reality, we face a choice. We can question our observations or we can question our rules. The observations came from multiple spacecraft. The data was cross-checked, verified, analyzed by teams working independently. The instruments were calibrated correctly. The processing was standard. The observations are real, which means the rules, or at least our understanding of them, might need revision. Avi Loeb, the Harvard astrophysicist who has spent years studying interstellar objects, calculated what power output would be required to produce this blue emission if it came from an internal heat source rather than solar heating alone. The numbers point to something generating energy at levels comparable to a nuclear power plant. But let's step back from the technical details for a moment and consider the poetry of what happened. For billions of years, this traveler moved through darkness, accumulating cosmic rays, witnessing distant explosions, silent and cold. Then, for a brief instant in cosmic time, a few hours, a few days, it passed close enough to our star to wake up, to remember what warmth feels like, to shine in colors it had perhaps forgotten or never known. And in that moment of communion between starlight and ancient ice, it did something we don't understand. It glowed blue like a memory, surfacing from deep time like recognition, like a message written in the only language that crosses the void intact, the language of light itself. Whether that message was intentional or accidental, whether it came from chemistry or consciousness, we cannot yet say, but the blue remains, the data remains. And somewhere in that impossible color lies a truth we're still learning how to read. Let's speak for a moment about scale, because scale matters when we're trying to understand what 3I Atlas truly is. The nucleus of this object, the solid core beneath its glowing coma, measures at least 5 kilometers in diameter. That makes it roughly the size of a small mountain or a large city. The mass estimates put it at 33 billion tons. To give you context, that's about 7 million times more massive than the International Space Station, humanity's largest structure in orbit. For a comet, this is enormous. Most comets are modest, a few hundred meters to maybe a kilometer across. The famous Halley's Comet is about 15 kilometers long, but it's irregular and fluffy. 3I Atlas appears more compact, denser, structurally robust, and it's traveling at speeds that dwarf anything humans have achieved. When discovered, it was moving at 61 kilometers per second, relative to the Sun about 137,000 miles per hour. As it approached perihelion, it accelerated to nearly 68 kilometers per second under the Sun's gravitational influence. At these velocities, the kinetic energy is staggering. If 3I Atlas were to collide with Earth, which it won't, its trajectory keeps it safely distant, the impact would release energy equivalent to millions of nuclear weapons. Not that this is a threat scenario. The object's hyperbolic orbit means it's passing through once and leaving forever. But the size and speed tell us something important about endurance. To survive millions or billions of years in interstellar space requires structural integrity. Cosmic rays degrade materials. Micrometeorite impacts chip away at surfaces. Temperature extremes, cold that would freeze steel, brittle, brief warmth from passing stars, stress any object over time. That 3I Atlas arrived here intact, coherent, not a rubble pile or debris field, suggests either unusual composition or unusual construction. Natural processes can produce durable objects. Metallic asteroids, for instance, can survive eons, relatively unchanged. But comets are typically fragile, loose aggregations of ice and dust, held together weakly by their own gravity. 3I Atlas behaves like a comet in some ways. It has a coma, it outgasses, it responds to solar heating. But it also behaves like something more robust, something built to last. There's a concept in astrophysics called sublimation death, the process by which comets gradually lose mass through outgassing until nothing remains. Every pass near a star strips away layers. The ice vaporizes, the dust blows away, and eventually the comet is gone, reduced to a thin stream of particles along its former orbit. This death is not violent. It's gradual, almost serene. The comet simply fades, its light dimming with each orbit until it becomes indistinguishable from the darkness it emerged from. But sometimes comet death is sudden. The nucleus fractures from thermal stress or rotational forces. It breaks into pieces, each piece heating and vaporizing faster than the original whole. The comet brightens dramatically, a final flourish before extinction. When 3I Atlas approached perihelion hidden behind the sun, many astronomers wondered if they would witness this kind of death. The previous interstellar comet 2I Borisov fragmented during its passage through our system. The stresses of solar heating overwhelmed whatever weak forces held it together, and it broke apart. The blue glow suggested something similar might be happening to 3I Atlas: intense outgassing, catastrophic mass loss, the beginning of the end. But when the object re-emerged from behind the sun, it was still intact, still coherent. The coma had changed, expanded, brightened, shifted in color, but the nucleus remained whole. This is not death. This is transformation. And there's a difference. Death implies ending closure, a final state from which there's no return. Transformation implies continuation, change without cessation, the same matter reorganized into new forms. 3I Atlas, in its passage past our sun, transformed. It took in energy, vast amounts of solar radiation, heating its surface, vaporizing its volatiles. And it released that energy in new forms, blue light streaming gas particles accelerating into space. The ancient ice formed billions of years ago in a stellar system we'll never visit, became light and motion in our sky. The molecules that spent eons frozen and still became kinetic, dynamic, radiant. And we were here to witness it. Humans, with our brief lives and our temporary civilizations, happened to exist at precisely the right moment to see this transformation, to catch this traveler in its moment of greatest activity, greatest brightness, greatest expression. That timing, cosmically improbable, yet it happened, feels less like luck and more like appointment, as if we were meant to see this. As if 3I Atlas, having wandered for millions of years, arrived exactly when someone was finally here to notice. Consider the mathematics of this encounter. The Milky Way galaxy is roughly 100,000 light-years across. Our solar system occupies a tiny region less than 1 light day in diameter. For 3I Atlas to pass through our specific neighborhood, out of all possible paths through the galaxy, requires a trajectory that intersects an almost infinitesimal fraction of space. And for us to be here technologically advanced enough to detect it, curious enough to study it at the exact moment it passes, that's another layer of improbability stacked on top. The universe is 13.8 billion years old. Human civilization has existed for about 10,000 years. We've had telescopes capable of detecting interstellar objects for less than a decade. The window where we could observe 3I Atlas spans just a few months. If it had arrived 100 years earlier, we would have missed it entirely. Our instruments weren't sensitive enough. If it arrives 100 years from now, we might have instruments so advanced that its anomalies would be immediately explicable. We're catching it in a sweet spot of human development, advanced enough to detect strangeness, primitive enough to still be confused by it. That sweet spot feels meaningful, like the universe calibrated this encounter for maximum educational value, maximum wonder, maximum mystery without complete incomprehensibility. Maybe that's the real communion, not between starlight and ice, but between consciousness and cosmos. Between beings who ask questions and a universe that occasionally provides spectacles worth questioning. between the young species just learning to look outward and the ancient traveler that passed close enough to be seen. In Hindu cosmology, there's a concept called darshan, the auspicious sight of the divine, the blessing received simply by seeing and being seen by something sacred. Pilgrims travel vast distances for darshan, to stand in the presence of something holy, to exchange a gaze. We don't have to accept religious frameworks to recognize something similar in our encounter with 3i Atlas. We traveled metaphorically built civilization, developed science, constructed telescopes to reach a point where we could see this traveler. And in seeing it, in directing our instruments and our attention toward it, we received something. Not answers necessarily, but presence, encounter, the knowledge that something else exists, something ancient and far-traveled and genuinely other. That exchange, our observation, its passage, might be the entire point. Not what 3i Atlas is, but that we noticed it, that we cared enough to look closely, that we built tools and institutions and collaborative networks capable of tracking an object across millions of miles, analyzing its light, debating its nature. If consciousness exists to witness the universe, then this moment is consciousness doing its work. And if the universe exists to be witnessed, then 3i Atlas passing through our observational range at precisely this moment in our development completes a circuit, closes a loop, fulfills some purpose that doesn't require intelligence to be meaningful. Maybe that's the real communion, not between starlight and ice, but between consciousness and cosmos, between beings who ask questions and a universe that occasionally provides spectacles worth questioning. Light is not simple. Light is archaeology. Every photon that reaches our telescopes carries information about its origin, where it came from, what it passed through, what processes generated it. By splitting that light into its component wavelengths using an instrument called a spectrograph, astronomers can read stories written in the very atoms of distant objects. When scientists analyzed the spectrum of 3i Atlas throughout its approach, they found something that challenges every model we have for how comets form and evolve: nickel emission. Lots of it. 4 grams every single second streaming away from the nucleus. To understand why this is strange, we need to talk about where elements come from: carbon, oxygen, nitrogen. The elements of life are forged in the nuclear furnaces of stars. During a star's lifetime, fusion reactions build progressively heavier elements. When the star dies, especially in a supernova explosion, these elements are scattered into space. They mix with hydrogen and helium from the Big Bang, condense into clouds, and eventually form new stars, planets, asteroids, and comets. Iron and nickel are particularly interesting. They're produced together in similar nuclear processes, always in roughly consistent ratios. The cosmic abundance of iron to nickel is about 18:1. You can find objects that are iron-rich or nickel-rich, but you cannot find nickel without at least some iron. The physics of stellar nucleosynthesis doesn't allow it. Until now. 3i Atlas shows strong nickel emission in its spectrum. Multiple observatories have confirmed it. The James Webb Space Telescope found it. The Very Large Telescope in Chile detected it. But iron, the element that should accompany nickel, is missing. Not depleted, not reduced. Missing. The upper limits on iron concentration are orders of magnitude below what should be there. The specific form of the nickel makes the mystery deeper. Spectroscopic analysis suggests the emission comes from nickel tetracarbonyl, a molecule consisting of 1 nickel atom bonded to 4 carbon monoxide groups. This compound is volatile, evaporates easily, breaks down under ultraviolet light into nickel atoms and carbon monoxide. On Earth, we manufacture it. The Mond process, developed in the 1890s, uses nickel tetracarbonyl to refine nickel to high purity. You expose impure nickel to carbon monoxide gas, nickel tetracarbonyl forms, you heat it, and pure nickel deposits out. It's industrial chemistry, something that happens in refineries and factories. Can it form naturally in space? Technically, yes, you need nickel grains, carbon monoxide gas, and the right temperature and pressure conditions. Carbon monoxide is common in comets. Nickel exists in cosmic dust. If a comet had an unusual concentration of metallic nickel grains embedded in its ice, and those grains were exposed to carbon monoxide, as the ice sublimated, some nickel tetracarbonyl might form. Might. But the concentration is the problem. We're not seeing trace amounts. We're seeing emission rates implying kilograms of nickel being released every day. That requires far more metallic nickel than cosmic abundances would predict. And it still doesn't explain the missing iron. There's a connection here that's easy to miss if you're focused too narrowly on individual anomalies. The blue color and the nickel emission are not separate mysteries. They're part of the same story. Nickel tetracarbonyl, when it breaks down under ultraviolet radiation, releases carbon monoxide. Carbon monoxide, when ionized, can produce blue emission. The blue glow might be coming from the same chemical process that's generating the nickel signal. Think of it like this. Imagine a mechanism, natural or otherwise, that concentrates nickel, stores it in a carbon monoxide-rich environment, then releases it when heated by the sun. The release produces both the blue glow we're seeing and the nickel spectral lines we're measuring. If this is a natural process, it's one we've never encountered before. It requires a formation environment completely unlike anything in our solar system, chemistry we don't understand, and a series of coincidences so specific that calculating their joint probability makes you question whether coincidence is the right word. But there's another interpretation. Dr. Gregory Rogers, a former U.S. Air Force flight surgeon and chief of aerospace medicine at Cape Canaveral, someone who has worked directly with spacecraft materials and hardware, said bluntly that the composition is impossible for natural objects. When we build satellites and space probes, we use nickel alloys. Not because nickel alone is ideal, but because nickel alloys have properties. We need corrosion resistance, high temperature strength, dimensional stability. If you were designing a spacecraft to survive millions of years in interstellar space to withstand cosmic radiation and temperature extremes, you might choose materials similar to what we choose: high nickel content, low iron to avoid magnetic interference or oxidation. And if that spacecraft were damaged, ablating material leaking volatiles stored in nickel alloy tanks, you might see exactly what we're seeing. Here's another piece of the chemical puzzle. 3I Atlas is remarkably dry. Normal comets are mostly water ice, typically 50 to 80% water by mass. Water is abundant in space. It forms easily in cold molecular clouds. Every comet we've studied in our solar system has water as its primary volatile component. 3I Atlas is only 4% water by mass, 4%. The rest is carbon dioxide, carbon monoxide, and various organic compounds, along with that mysterious nickel. A comet this dry is not unheard of, but it's rare, and it's convenient in a way that raises questions. Water is heavy. If you're designing a propulsion system that vaporizes stored volatiles for thrust, you might choose carbon monoxide or carbon dioxide over water. They provide better specific impulse, more thrust per unit of propellant mass. They're more efficient. The low water fraction makes 3I Atlas a worse comet by natural standards. By the standards we use to understand how icy bodies form in stellar systems, an object this dry is an outlier, an anomaly. But by engineering standards for a spacecraft that needed to carry fuel across interstellar distances, an object with this composition would be optimal. You'd minimize water, heavy inefficient, and maximize lighter volatiles that give you more bang for your buck. This is speculation, of course. But it's speculation that fits multiple pieces of data simultaneously: the composition, the acceleration, the structural integrity. But let's not lose ourselves entirely in speculation. Let's return to what light teaches us about humility. The spectrum of 3I Atlas tells us that something about our understanding is incomplete. Either comets can form in ways we never imagined in molecular clouds, with bizarre chemistry and stellar systems nothing like ours, under conditions that produce nickel without iron and blue without sufficient heat. Or we're looking at something that formed not in a nebula but in a design facility, not through accretion and collision but through purpose and engineering. The light doesn't tell us which. The light only tells us something here doesn't match the patterns you expected. And that's the thing about light, it's honest. Photons don't lie. They don't care about our theories or our comfort. They arrive carrying their stories, and we either learn to read them or we stay confused. The blue of 3I Atlas is not just an anomaly. It's an invitation to sit with uncertainty, to acknowledge that the universe is larger and stranger than our current frameworks can contain, to remain curious rather than defensive when confronted with the inexplicable. One researcher described the blue as possibly representing ionized carbon monoxide, a natural if unusual explanation. Another suggested it could indicate artificial light sources or excess heat from an internal engine. Both are attempting to read the same light, the same spectrum, the same data. The difference lies not in the photons, but in what we're willing to imagine. Throughout human history, blue has carried meaning. The ancient Egyptians synthesized the first blue pigment, Egyptian blue, by heating silica, copper, and calcium. They used it in art and funerary objects, associating the color with the heavens and the life-giving Nile. The pigment was so valued that it appears on the funerary mask of Tutankhamun on temple walls, depicting gods in the delicate paintings of papyrus documents meant to guide souls through the afterlife. The Maya created Maya blue, a pigment so chemically stable that artifacts painted with it 1,500 years ago still shine vibrant today. They used it in sacred rituals, painting sacrificial victims and ceremonial objects. The pigment involved a complex process, mixing indigo plant dye with a specific clay mineral, heating it to exact temperatures. Modern chemists still study how the Maya achieved such permanence, such resistance to time and decay. In medieval Europe, blue was the color of the Virgin Mary, of divinity, of truth. Artists ground lapis lazuli, a stone rarer than gold, imported from mines in Afghanistan along treacherous trade routes, into ultramarine pigment for their most important works. Only the wealthiest patrons could afford paintings with extensive blue. To paint Mary's robes in ultramarine was to demonstrate devotion through extravagance, to honor the divine with the most precious earthly materials. In Japan, indigo dyeing became an art form spanning centuries. The deepest blues were called Japan blue, colors so rich they seemed to hold depth dimension mystery. Artisans would dye fabric multiple times, sometimes 50 applications or more, to achieve the perfect shade. The process required patience, skill, and understanding of fermentation and chemistry that predated modern science. Navajo peoples associate blue with the south, with turquoise with the sky at noon. In their creation stories, blue represents one of the 4 sacred colors, corresponding to one of the 4 sacred mountains that define their traditional homeland. Blue is not just aesthetic, it's directional, spiritual, fundamental to understanding one's place in the landscape. And across virtually every culture, blue has symbolized distance and vastness, the color of sky and deep water, the color of things beyond reach. We speak of feeling blue, of blue moods, associating the color with melancholy perhaps, because it's the color of infinity, of spaces we cannot cross, of the unreachable. When 3I Atlas turned blue at perihelion, it tapped into something primal in human perception. We recognize blue as special, as rare, as meaningful. Even without understanding the physics, we feel the significance. An interstellar visitor glowing blue against the solar corona speaks to something deeper than spectroscopy. It speaks to our oldest associations between color and mystery, between rare beauty and the sacred unknown. There's a neurological reason blue affects us so deeply. Human eyes contain 3 types of cone cells, each sensitive to different wavelengths, but we have fewer blue-sensitive cones than red or green. Blue is literally harder for us to see, requires more effort to process. When we see pure saturated blue, our visual system is working near the edge of its capability. This might explain why blue feels more ethereal, more otherworldly than other colors. We're seeing something our eyes are barely equipped to perceive. It exists at the boundary of our sensory capacity, the way certain musical notes exist at the edge of hearing, the way certain ideas exist at the limit of comprehension. Three-eye atlas glowing blue, in a way that defies physics, became not just scientifically anomalous, but perceptually significant. It appeared in a color that our eyes recognize as liminal, as boundary space between the visible and the invisible. And maybe that's part of what we're really responding to in this moment. Not just the scientific puzzle of an impossible color, but the aesthetic and symbolic resonance of blue, that particular blue appearing in our sky, from an object older than our species, traveling distances our minds can barely comprehend. The universe in its vast indifference accidentally created a moment of meaning. Or perhaps meaning is what consciousness does when confronted with the inexplicable. We find significance, we assign value. We weave stories that help us bear the weight of cosmic mystery. The color blue carries the weight of 30,000 years of human culture. Every time an Egyptian priest mixed pigment, every time a European artist ground lapis, every time a Japanese artisan dipped fabric in indigo, every time a child looked up at the sky and asked, "Why is it blue?" All of that history, all of those associations, all of that accumulated meaning converges when we see Three-Eye Atlas glowing impossibly blue against the sun. We're not just observing an astronomical phenomenon, we're witnessing a moment where science, culture, perception, and history intersect, where an ancient traveler from the depths of space happens to manifest in the exact color that humans across every culture have recognized as sacred, as special as the color of distance and divinity. Either way, the blue remains. And so does the question of what it means, if it means anything at all beyond the quantum mechanics of excited molecules and the evolutionary history of human vision. But perhaps beyond is the wrong preposition. Perhaps the meaning is in all of it, the physics and the perception, the culture and the chemistry, the ancient pigments and the ancient comet, all resonating at a frequency that spans from individual molecules to entire civilizations. Blue, the color that connects Egyptian tombs to Japanese textiles, to Virgin Mary's robes, to the depths of ocean, to the interstellar visitor that shouldn't be that color at all. There is something unsettling about motion without visible cause. We are creatures of cause and effect. We understand that objects move because something moves them. A ball rolls because someone kicked it. A planet orbits because gravity pulls it. The entire edifice of physics rests on this foundation. Forces produce accelerations, and accelerations change velocities. When something moves without an apparent force, we don't immediately doubt physics. We assume we're missing something. There's a force, we haven't identified a mass, we haven't accounted for an interaction we haven't measured. But what happens when we account for everything we know and the motion still doesn't make sense? On October 27, 2025, NASA published a technical document. No press release, no announcement, just dry orbital mechanics showing something that shouldn't be there. Three-Eye Atlas is experiencing non-gravitational acceleration. The object is changing velocity in ways that cannot be explained by gravity alone. Let me explain what non-gravitational acceleration means, because the term itself can be misleading. Every object in our solar system moves according to gravitational fields. The sun's gravity dominates, pulling everything toward it, but planetary masses add smaller perturbations. Given an object's position and velocity at any moment, astronomers can calculate its future trajectory with extraordinary precision. This is how we navigate spacecraft across billions of kilometers. But comets behave slightly differently than inert rocks. When ice vaporizes from a comet's surface, Gas jets away into space, and Newton's third law applies action and reaction. The escaping gas pushes the comet in the opposite direction. This rocket effect is well understood and entirely natural. We see it in every active comet. The question with 3I Atlas isn't whether it experiences non-gravitational forces. The question is whether the forces we observe match what natural outgassing should produce. NASA's analysis detected two distinct components: radial acceleration pointing away from the Sun at 135 kilometers per day, squared, and transverse acceleration perpendicular to the Sun's direction at 60 kilometers per day, squared. The radial component makes sense. Solar heating warms the sunward side ice sublimates preferentially in that direction. The rocket effect pushes outward. Standard behavior. The transverse component is harder to explain naturally. To produce transverse acceleration through outgassing alone requires either extremely asymmetric jets or very specific rotational configurations. But we haven't detected the kind of brightness variations that would indicate such dramatic asymmetry. The light curve is too smooth, and then there's the magnitude of the acceleration itself. Avi Loeb calculated what these accelerations imply about mass loss. For 3I Atlas to generate the observed thrust through outgassing alone, it would need to shed approximately 15% of its total mass over the coming months. We're talking about billions of tons of material. That's not gentle sublimation. That's catastrophic. That's the kind of mass loss you see when structural integrity fails when a comet breaks apart. Yet 3I Atlas isn't fragmenting. Imaging shows a coherent nucleus. The coma structure remains organized. There's no debris field. So we have an object that's accelerating, as if it's violently outgassing while not showing evidence of violent outgassing. An object that should be disintegrating but isn't. An object that should be falling apart but holds together. Unless the acceleration isn't from passive outgassing at all. Unless something is actively thrusting. 3I Atlas reached perihelion on October 29th. In orbital mechanics, perihelion is the optimal point for maneuvers. When you're deep in a gravity well moving fast, thrust is most efficient. A velocity change at perihelion translates to a much larger change in orbital energy than the same thrust applied elsewhere. Every spacecraft engineer knows this. Every mission that has done a gravity assist has exploited this principle. If you were an interstellar probe and needed to adjust your trajectory to pass close to specific planets, to achieve certain observational geometries, to position yourself for the next phase of your mission, you would fire your engines at perihelion. The non-gravitational acceleration parameters changed after perihelion. Not dramatically, not like a sudden throttle, but measurably. The kind of change you might see if a propulsion system activated, made a burn, then throttled back. I want to be careful here. This is speculation, but it's speculation that fits the data. The natural explanation requires us to believe that a comet is behaving in unprecedented ways, accelerating without fragmenting outgassing, without the expected spectroscopic signatures maintaining structural integrity under forces that should destroy it. The artificial explanation requires us to believe something built this object and sent it here. Both beliefs require a leap, but the direction of the leap matters. There's something deeply human about restless motion. We are not still creatures. Even in sleep we shift and turn. Even at rest our cells burn energy, our neurons fire, our hearts beat out their endless rhythm. To be alive is to be in motion directed by forces we don't fully control. Hunger, curiosity, fear, love, the simple need to see what's beyond the next hill. 3I Atlas. Accelerating through space for reasons we can't fully explain feels like a cosmic mirror to something in us. Maybe that's why this story has captured imaginations beyond the astronomy community. Maybe it's not really about aliens or comets. Maybe it's about recognizing in this distant ancient traveler the same restlessness we feel, the same drive to move, to explore, to push against the gravitational wells that would hold us in place. Avi Loeb has argued that the acceleration combined with the object's trajectory past multiple planets suggests fine-tuning. Small corrections that optimize encounters, that steer toward specific targets. Whether that fine-tuning comes from intelligence or from the blind mathematics of orbital dynamics, the effect is the same motion that seems purposeful, that seems directed, that seems to know where it's going. And perhaps that's what unsettles us most. Not that 3i Atlas might be artificial, but that it might have purpose in a universe we've assumed operates without intention. Because if purpose exists out there independent of us, then we're not the authors of meaning we thought we were. This isn't the first time humanity has struggled to explain celestial motion. In the 2nd century, C.E. Ptolemy proposed his geocentric model of the universe Earth at the center, everything else moving in complex circular paths called epicycles. The planets sometimes appeared to move backward against the background stars, an optical illusion we now call retrograde motion. To explain this, Ptolemy added circles within circles mathematical constructs that described the motion but didn't explain it. The model worked after a fashion. You could predict where planets would be with reasonable accuracy, but it was complex, unwieldy, requiring constant adjustment. Then Copernicus proposed heliocentrism: sun at the center Earth and planets orbiting it. Suddenly, retrograde motion made sense. It was simply a consequence of Earth overtaking slower outer planets in our respective orbits. The complexity dissolved into elegant simplicity. But even Copernicus assumed circular orbits. It took Johannes Kepler to realize that planetary orbits are elliptical, not circular. And it took Newton to explain why gravity provides the force that curves their paths. Each step was a conceptual leap, a willingness to abandon assumptions to see familiar phenomena in new ways. With 3i Atlas, we might be at a similar juncture.
We have a model comet's outgas creating rocket effects. It works for most cases, but this case doesn't fit cleanly. We can add epicycles, unusual chemistry, strange rotation, unprecedented composition, and make the numbers work after a fashion. Or we can ask if there is a simpler explanation we're avoiding, because it requires too great a conceptual leap. The motion continues, regardless of how we explain it. The acceleration persists, whether we attribute it to outgassing or propulsion. Reality doesn't wait for our theories to catch up, and so we're left, as humans have always been left, when confronting cosmic puzzles, with observations that challenge understanding, with data that suggests something new, with a choice between comforting complexity and uncomfortable simplicity. History suggests that truth usually lies in the direction of elegance. Occam's razor cuts toward parsimony.
The explanation that requires fewer assumptions that connects more phenomena under a single framework tends to be correct. But history also teaches us to be careful about what we assume away. The universe has no obligation to be simple just because we prefer it that way. We're still learning the grammar of this motion, still trying to parse the forces that drive it. The data will keep coming. The trajectory will keep updating. And somewhere between the equations and the observations, between what gravity demands and what chemistry allows, lies an answer we're still teaching ourselves how to ask for. For now, we can only watch as 3i Atlas continues its journey, accelerating, adjusting, moving through our solar system with a determination that might be physics or might be something more. Either way, it's moving, and motion, as we know from our own restless lives, is rarely without reason. Let me tell you something true about human beings. We invent mysteries not to escape reason, but to feel less isolated in the vastness. When ancient peoples looked at the patterns of stars and saw hunters bear scorpions, they weren't being childish or primitive. They were doing what humans have always done, reaching across the terrible distance between self and other, trying to find connection, trying to write themselves into the cosmos so the cosmos wouldn't feel so empty. The conversation around 3I Atlas has fractured the scientific community, but beneath the technical arguments lies something more primal, a hope, a fear, a question that every conscious being asks eventually, are we alone? Avi Loeb says it openly. This might be artificial, a spacecraft, technology from another civilization. He presents his probability calculations, his 9 anomalies, his 1 in 10 quadrillion odds, and he says clearly what most scientists only whisper: we should take this possibility seriously. The backlash has been swift and fierce. His colleagues call him sensationalist, attention-seeking, undermining scientific credibility. They say he's jumping to conclusions, ignoring natural explanations, playing to conspiracy theorists. But here's what interests me more than the argument itself, the emotion behind it. Why does suggesting extraterrestrial intelligence trigger such strong reactions? It's not because the idea is absurd. Every astronomer acknowledges that life almost certainly exists elsewhere. The universe is too vast, stars, too numerous planets, too common for Earth to be unique. Most scientists believe intelligence has arisen many times in the 13.8 billion years since the Big Bang. The resistance isn't to the possibility, it's to the implication. Because if 3I Atlas is artificial, if it was built and sent here by something that thinks, that plans, that explores, then several comfortable assumptions collapse immediately. First, we are not the most advanced intelligence in the universe, probably not even close. Whatever built this has been traveling between stars for millions of years while we were still figuring out fire. Second, they're here, not in some abstract, far-distant corner of space, but here in our solar system, close enough to study, close enough to potentially observe us. Third, they haven't announced themselves in the way we expected. No massive radio transmission, no fleet of ships, no contact, just this silent visitor collecting data, perhaps watching, perhaps then leaving, which raises the question, why not say hello? These implications are uncomfortable. They make us feel small, observed, evaluated, maybe found wanting. Social media exploded when Elon Musk weighed in, suggesting the anomalies deserve serious attention. Kim Kardashian asked NASA if we should be worried, receiving a carefully worded response: no aliens, no threat to Earth. This is where science and culture collide. The data says something strange is happening. Different interpreters see different patterns. Some see a comet with unusual chemistry. Others see evidence of design. And the public people without advanced degrees, without telescopes, without access to the raw data, feel something in this moment. They feel the possibility. They feel the weight of what it would mean. I've read the comments, thousands of them. They break into camps, those who desperately want it to be artificial, who see in 3I Atlas a cosmic rescue from insignificance, proof that the universe is populated and knowable and filled with beings we might someday meet. Those who desperately want it to be natural, who find comfort in a universe that operates by predictable laws, where anomalies resolve into better models, where we remain the masters of our scientific understanding. And those in the middle, uncertain, curious, willing to wait for more data while holding both possibilities in suspended judgment. Here's the thing about 3I Atlas. As a mirror, it reflects what we bring to it. If you come to this mystery hoping for aliens, you'll find 9 anomalies that suggest design. If you come hoping for natural explanations, you'll find ways that comets might behave in unprecedented but explicable ways. The photons don't care which interpretation comforts you. The nickel keeps emitting. The acceleration continues. The blue glow happened regardless of what anyone believes about it. But we're not just passive observers recording data. We're participants in meaning-making. Every choice about which anomaly to emphasize, which explanation to favor, which expert to trust, these choices reveal our underlying hopes and fears about the universe we inhabit. The astronomy community is experiencing what one observer called a civil war, with Loeb on one side demanding that artificial hypotheses be taken seriously, and the establishment on the other insisting we exhaust natural explanations first. Both sides are right, both sides are wrong. Science demands skepticism, especially of extraordinary claims. But science also demands openness to evidence that challenges the paradigm. The tension between these demands is healthy. It's how knowledge advances. What's not healthy is when the argument becomes about tribe and territory rather than truth, when disagreement turns to dismissal, when curiosity gets punished for wandering too far from consensus. There's an empathy in this moment that's easy to miss amid the technical debates. Every person watching this unfold, whether scientist or student skeptic or believer, is participating in something profound, the human attempt to understand our place in existence. When Avi Loeb says Three-Eye Atlas might be artificial, he's not just making a scientific claim. He's giving voice to a longing that millions feel, the longing for confirmation that we're not alone, that intelligence is common, that the universe is populated with minds capable of recognizing other minds. When his critics push back, they're not just defending scientific rigor. They're expressing a different kind of hope, that we still have time to be the first, that the universe is still ours, to explore without competition or comparison, that we haven't been watched and judged already. Both longings are valid. Both deserve acknowledgement. Maybe what Three-Eye Atlas is really teaching us isn't about comets or spacecraft. Maybe it's teaching us about ourselves, about how we handle ambiguity, how we respond to the unknown, how we treat each other when confronted with questions that don't have easy answers. Because here's the truth. Whether Three-Eye Atlas is natural or artificial, we're still alone in the way that matters most. We're alone with our choices, our interpretations, our responsibility to seek truth with humility and courage. The universe doesn't owe us clarity. It owes us nothing. But we owe ourselves honesty about what we see and why we see it that way. Let's talk about Carl Sagan for a moment. Sagan spent decades searching for extraterrestrial intelligence. He sent messages into space, the Arecibo transmission, the Voyager golden records. He believed passionately that life exists elsewhere, that contact is possible, that meeting another intelligence would transform humanity. But he was also rigorous. He demanded evidence. He fought against pseudoscience, against accepting claims without verification. His famous quote, "Extraordinary claims require extraordinary evidence," became a mantra for skepticism. Sagan would have loved Three-Eye Atlas. He would have been fascinated by the anomalies, excited by the possibility, insistent on careful analysis. He would have held both wonder and skepticism in the same breath, modeling how to be curious without being credulous. That balance, wonder and rigor, openness and skepticism, is what we need now. Not blind belief in alien spacecraft, not reflexive dismissal of anything that challenges consensus, but the willingness to sit with uncertainty, to follow evidence, even when it's uncomfortable, to remain open to the possibility that the universe is stranger than our current frameworks allow. And maybe that's the gift of ambiguity. It forces us to examine our assumptions, to sit with uncertainty, to recognize that reality doesn't care about our comfort or our narratives.
Atlas continues its journey indifferent to what we believe about it. The only question is whether we can match that indifference. Can we observe without needing it to be one thing or another? Can we hold the mystery without collapsing it prematurely into an answer? December will bring more data, more observations, more clarity, but it won't bring certainty, not completely, and perhaps that's precisely what we need. A reminder that the universe is larger than our ability to fully explain it, stranger than our models can capture, and worthy of wonder regardless of whether it confirms or challenges what we hoped to find. There's a particular quality to institutional silence that differs from absence of information. It's heavier, more deliberate, it carries weight. On October 2nd and 3rd, 2025, NASA's Mars Reconnaissance Orbiter observed Three-Eye Atlas from just 30 million kilometers away using its high-rise camera.
The resolution 30 centimeters per pixel, 3 times better than the best Hubble images. These photographs could potentially show surface features, compositional variations, structural details that might answer definitively what this object is. As of early November, those images have not been released. The data sits in NASA servers while the scientific community waits. The government shutdown that began October 1st, the same day as these crucial observations, has frozen data sharing across multiple missions. Avi Loeb went on the Joe Rogan Experience and talked about this silence. His frustration was visible. He explained how he'd requested the high-rise data, how Congresswoman Anna Paulina Luna had written a formal letter to NASA's acting administrator demanding release, how the shutdown was being used as justification for withholding public information. But let's sit with the silence itself for a moment before rushing to judgment about its cause. Silence can mean many things.
It can mean bureaucratic dysfunction, furloughed workers, frozen protocols, systems designed for normal operations failing under crisis conditions. It can mean caution, administrators uncomfortable releasing data that might generate controversy, waiting for clarity, seeking guidance from higher authorities who are themselves unavailable. It can mean active suppression, though this seems least likely, given that suppressing scientific data in the age of international collaboration and multiple independent observers is nearly impossible. Or it can mean nothing at all, just the ordinary delays that afflict any large organization, amplified by unfortunate timing. Here's what the silence is teaching me. Patience is part of the practice of knowing. We live in an era of instant information. Questions asked are answered within seconds. Mysteries posed in the morning are solved by evening.
We've trained ourselves to expect immediate resolution, immediate clarity, immediate satisfaction of curiosity. But the universe operates on different time scales. Light from 3I Atlas takes minutes to reach Earth even when the object is at its closest. The signals NASA's Mars orbiters send home travel at the speed of light but still require minutes to arrive. Processing data, verifying results. Preparing releases, these take hours, or days even under optimal conditions, and those are the fast timescales. On longer scales, the comet itself has been traveling for millions or billions of years. Human civilization is 10,000 years old. Modern astronomy is barely a few centuries old. We've been seriously looking for interstellar objects for less than a decade. The universe is patient. It has no deadlines, no hurry, no obligation to reveal its secrets on our schedule. There's a valuable practice in simply sitting with questions that lack immediate answers. In meditation, teachers often speak of the don't know mind, the state of being comfortable with uncertainty, of holding questions without grasping for premature resolution. The opposite of this is the knowing mind, which rushes to conclusions, closes inquiry, prefers bad answers to good questions. 3I Atlas is inviting us into don't know mind. We don't know what caused the blue color. We don't know why the nickel concentration is so high. We don't know if the acceleration implies propulsion or just unusual outgassing. We don't know when or if NASA will release the high-rise images. And in that not knowing, there's freedom. Freedom from the anxiety of needing to be right. Freedom from the pressure to pick a side in the debate. Freedom to simply observe, to remain curious, to let the mystery unfold at its own pace. Consider the 1977 WOW signal. For a moment, the powerful radio burst detected by the Big Ear telescope, lasting exactly 72 seconds, never repeated, despite decades of searching. If that signal was artificial, if it was an attempt at contact our species responded with, nothing coherent. We noticed it, we wrote "wow" on a printout, and then we moved on. The telescope that detected it was eventually demolished to build a golf course. If someone was trying to get our attention, our response must have seemed like silence from their perspective, like indifference, like we weren't paying attention or didn't care. Maybe NASA's current silence around the high-rise images is the universe reflecting our own behavior back to us. teaching us what it feels like to wait for answers that don't come on the schedule we expect, teaching us what it's like to send signals into the void and receive no immediate response. Silence in this view isn't absence, it's presence of a different kind. It's the space where patience is cultivated, where assumptions are examined, where we learn whether we're truly ready for the answers we claim to seek. The December observations will come. The high-rise images will eventually be released one way or another. More data will accumulate. The mystery will move towards some form of resolution, though perhaps not the clean, definitive resolution we want. In the meantime, we wait, and maybe that waiting is itself valuable. Maybe the gap between question and answer is where wisdom lives. Maybe rushing to conclusion, any conclusion, would rob us of the opportunity to sit with genuine cosmic mystery in an age when mysteries feel increasingly rare. There's a difference between the silence that comes from concealment and the silence that comes from reverence, between the quiet of hiding and the quiet of listening. I don't know which kind of silence we're experiencing with 3i Atlas, maybe both, maybe neither. But I know that silence, when approached with patience rather than paranoia, can teach things that noise never could. It can teach humility. We don't control the flow of information or the pace of revelation. It can teach perspective. Our urgency is not the universe's urgency. It can teach presence. The moment between question and answer is just as real, just as worthy of attention as the moment when clarity finally comes. So we wait. Not passively, not with resignation, but with active attention. Watching for the next data release. Preparing for December observations, staying curious without demanding immediate satisfaction. The silence won't last forever. But while it does, it's teaching us something about how to be human in a universe that refuses to follow our scripts. And maybe that's enough. Let's reimagine what happened at perihelion. The narrative we've been carrying that 3i Atlas might have exploded or blown apart contains an assumption about destruction that might be entirely wrong. What if what we witnessed wasn't death, but birth, not ending, but beginning? Not a comet breaking under stress, but a comet releasing what it carried all along. Think about how life spreads on Earth. A dandelion doesn't die when it releases its seeds to the wind. It transforms. The flower that was singular becomes plural, hundreds of seed heads drifting on air currents, each carrying the potential for new growth. The parent plant isn't destroyed, it's distributed. Many trees produce seed pods that crack open violently, flinging seeds in all directions. The plant isn't killing itself, it's maximizing the geographic spread of its offspring. Ocean-dwelling creatures like jellyfish reproduce by fragmentation. A single jellyfish polyp can split into dozens of ephrae, each becoming an independent organism. The original polyp didn't die, it multiplied. What if 3i Atlas works similarly? What if the breaking apart we worried about, the catastrophic mass loss calculations suggested the fragmentation that should have occurred? What if all of that was always part of the design? Not a failure, but a feature. Consider the engineering challenge of interstellar exploration. You want to study a solar system, multiple planets, diverse environments, various distances from the star. Sending one large probe to visit each planet sequentially would take decades, maybe centuries. The mission would age, systems would degrade, and you'd gather data slowly. But if you sent one mothership that could deploy smaller probes at optimal moments, each specialized, each targeted to a specific destination, you could observe an entire solar system simultaneously. Parallel data collection, multiple vantage points, redundancy in case any individual probe fails. The deployment would ideally happen at perihelion when the sun's gravity provides maximum assist, when small velocity changes translate into large orbital differences. You'd time it precisely, release your payload, and let orbital mechanics do the work. From Earth watching this happen, what would we see? We'd see a single object approaching the sun. We'd see it brighten dramatically as it neared perihelion. We'd see it disappear behind the sun's glare, and when it emerged, we'd see What a debris field, multiple smaller objects. Or perhaps the deployment would be subtle enough that we wouldn't see it at all with our current instruments. There's a philosophical principle here worth contemplating. In Buddhist thought, there's the concept of anatta non-self, or the idea that what we perceive as singular entities are actually collections of components with no inherent unified identity. A person isn't a fixed self, but a constantly changing aggregation of cells, thoughts, experiences. In quantum physics, we talk about wave-particle duality, light behaving as both wave and particle depending on how we observe it. The question, what is light, doesn't have a simple answer. It depends on context, on measurement, on the frame of reference. 3i Atlas might be teaching us something similar about identity and continuity. Was it ever really one object, or was it always a collection of components traveling together, held by weak forces awaiting the right moment to diverge into independent trajectories? If it released probes at perihelion, did 3i Atlas die? Or did it simply become more honest about what it always was, many things traveling together for a while, then separating to pursue different destinies? Every shard of a broken comet carries information about the whole. When scientists study meteorites, fragments of asteroids that have fallen to Earth, they're analyzing pieces of objects that broke apart long ago. Each meteorite tells a story about formation conditions, about the chemistry of the early solar system, about processes that shaped our cosmic neighborhood billions of years ago. The fragments are as valuable as the intact object would have been, sometimes more so because breaking apart exposes internal structure that was hidden when everything was whole. If 3i Atlas fragmented, each piece carries a record. The chemical composition, the isotopic ratios, the structural properties, all preserved, all available for study if we can observe closely enough. But there's another kind of information that fragments carry: intention. If you were designing a probe to study our solar system and you wanted to maximize your data collection, you wouldn't keep everything together. You'd fragment deliberately. Each piece would have a mission. Each piece would be a message in itself, carrying instruments, carrying samples, carrying whatever you wanted delivered to specific locations. The fragments wouldn't be debris, they'd be emissaries. Let's think about this from an information theory perspective. Claude Shannon, working at Bell Labs in 1948, founded information theory by asking a simple question: how do you transmit messages reliably through noisy channels? His answer revolutionized communication redundancy. You encode the message multiple times, send it through multiple channels. Use error correction codes that allow reconstruction even if parts are lost. The Mars rovers use this principle. Curiosity and Perseverance don't send data once. They send it multiple times through multiple antennas at multiple times of day. NASA wants to ensure that important discoveries aren't lost because a single transmission failed. If you're sending information across interstellar distances, across millions or billions of years, Shannon's principles apply even more urgently. You can't risk a single point of failure. You can't put all your data, all your samples, all your instruments in one fragile package. You fragment. You distribute. You ensure that even if 90% of your mission fails, the remaining 10% can complete essential objectives. From Earth, watching this strategy unfold, fragmentation looks like catastrophic failure, but from a systems engineering perspective, it's resilience, it's redundancy. It's the best way to ensure mission success across timescales where accidents and failures are inevitable. Consider the biological parallel spores. Fungi reproduce by releasing millions of tiny spores into the air. Each spore is a potential new fungus, carrying the complete genetic information needed to start a colony. Most spores fail, they land in hostile environments, dry out, get eaten, never germinate. But the strategy works because even a tiny success rate multiplied by millions of attempts results in propagation. The mushroom doesn't break apart in failure when it releases spores. It achieves its evolutionary purpose. The visible fruiting body, the part we call a mushroom, is just the reproductive structure. The main organism is the mycelial network underground, which persists whether the mushroom succeeds or fails. If 3i Atlas is artificial, maybe the large visible object is like the mushroom, the delivery system, the fruiting body, the part designed to be seen. And the actual organism, the mission, the data collection network. The intelligence is what gets released, what becomes distributed, what persists even after the parent body is gone or departed. We're watching the mushroom and asking, is it dying? When we should be asking, what is it releasing and where are those spores going? There's also a principle from distributed computing, Byzantine fault tolerance. In networked systems where some nodes might fail or even behave maliciously, you design systems where consensus can still be reached, where the network continues functioning even if a significant percentage of nodes are compromised. You do this through redundancy, through voting mechanisms, through multiple pathways for information flow. An interstellar mission faces similar challenges. You can't predict what will fail. You can't know which instruments will survive, which will malfunction, which will encounter environments they weren't designed for. So you build redundancy into the architecture itself. Multiple probes, each semi-autonomous, each capable of basic functions, each carrying copies of critical information. If one fails, the others continue.
If communication between them is lost, each can still complete its mission independently. The system degrades gracefully rather than failing catastrophically. This is sophisticated engineering. This is how you build systems meant to last millions of years, to cross distances where real-time control is impossible to operate in environments you can't fully predict. And from our perspective, watching such a system deploy, it would look like a comet breaking apart at perihelion, multiple objects scattering on different trajectories, each piece going its own way, apparently independent, apparently uncontrolled. Unless they're not uncontrolled, unless each piece knows exactly where it's going. Now consider what each fragment might carry if this scenario is even partially correct. Scientific instruments, obviously. Spectrometers to analyze planetary atmospheres, cameras to image surfaces, particle detectors to measure solar wind and cosmic rays, seismometers to study internal structure if any fragment impacts a body, magnetometers to map magnetic fields. Each probe specialized for different observations together, providing comprehensive data about the entire solar system, but maybe more than instruments. Maybe samples. If 3i Atlas traveled for billions of years, it passed through regions of interstellar space we'll never reach. It might carry dust from other stellar systems, ice that formed in molecular clouds with different chemistry than ours. Maybe even biological material if life exists elsewhere and survives in frozen form. If fragments impact planets or moons in our solar system, they deposit those samples. Contamination from our perspective, panspermia from theirs. A way of sharing genetic or chemical information between stellar systems using comets, as seed pods using gravity to deliver payloads to interesting locations. Or maybe information in more direct forms.
Memory storage if they have technology for long-term data preservation. Cultural artifacts if they want to communicate who they are. Mathematical or scientific constants encoded in physical structures like the hydrogen line frequency they might have used for the wow signal but written in matter rather than radio waves. Each fragment becomes a library, a museum, a message in a bottle cast across the cosmic ocean. The ancient Library of Alexandria was destroyed by fire. All that knowledge, geometry from Euclid astronomy, from Hipparchus poetry, from Sappho medical texts, from Herophilos, much of it lost forever because it existed in only one place. Civilizations since have learned. We distribute knowledge now, multiple copies in multiple locations. The internet is redundant by design. Important cultural artifacts are digitized and stored in multiple archives. The Svalbard Global Seed Vault in Norway preserves seeds from around the world in case of agricultural catastrophe. If you're a civilization capable of interstellar travel, you've learned this lesson too. You don't put all your knowledge, all your cultural heritage, all your scientific achievements in one place. You send it out. You fragment it. You ensure that even if your home world is destroyed, even if your civilization ends, something survives. Someone might find it. Someone might learn from it. Someone might remember you. Maybe that's what 3i Atlas is, a fragment of someone else's Svalbard vault. A piece of someone else's distributed archive. Not a probe studying us, but a library seeding itself across the galaxy, hoping that somewhere, someday, someone will read what it carries. And we're here right now at the exact moment when that library passes through our system, when we're advanced enough to notice it, but still innocent enough to wonder what it is. Whether any of this is true or all of it is fantasy, the principle remains: fragmentation is not always failure. Sometimes it's strategy, sometimes it's success. Sometimes it's the only way to ensure that anything survives the journey. 3i Atlas came from distance beyond measure, glowed briefly in our sky, and may have scattered itself across our solar system in ways we won't detect for years or decades. And if it did, each fragment carries a piece of the story. Each shard remembers the whole. Each messenger, if that's what they are, knows its mission. We just have to find them. We just have to learn how to read what they carry. And maybe somewhere in those fragments is an answer to the question we've been asking since we first looked up at stars: are we alone? Here's a lesson from ecology scattering: is resilience. Species that concentrate in one location are vulnerable. One disaster, disease, drought, predation can destroy the entire population. But species that scatter, that spread across diverse habitats, survive. The loss of one group doesn't mean extinction. Others persist, adapt, eventually repopulate. This strategy works in information systems too. Distributed networks are more robust than centralized ones. If you want data to survive, you don't put it all in one place. You fragment it, replicate it, distribute it across multiple nodes. If 3i Atlas was carrying anything, data, instruments, biological samples, cultural artifacts from whatever civilization might have sent it, fragmenting at perihelion would ensure survival. Even if one piece is destroyed or lost, others continue. The mission persists through its distributed components. From our perspective, this looks like breaking apart. From a systems design perspective, it looks like redundancy, like wisdom, like something that understands how to endure across cosmic timescales. Let's bring this back to human experience, because we understand renewal in our own lives. Every 7 years, most of the cells in your body are replaced. The atoms that made up you in childhood are no longer present. You're materially a different person, reconstructed gradually from food, water, air. Yet you maintain continuity. You're still you, same memories, same identity, same sense of self, despite being physically different matter. Or consider relationships. Friendships that were close become distant. People we loved drift away. But new connections form. New intimacies develop. The community that surrounds us is always changing, always being rebuilt, fragments departing and new elements arriving. This is the human experience of being a broken comet. We're constantly fragmenting and reforming, losing pieces of ourselves and gaining new ones, maintaining identity through change rather than through stasis. When we see 3i Atlas potentially breaking apart, maybe we're seeing our own reflection. Maybe we recognize in its fragmentation the same process of transformation that governs our own lives. And if we can find meaning and continuity in our own constant renewal, perhaps we can extend that understanding to an ancient traveler doing the same thing on a cosmic scale. There's a Japanese aesthetic principle called wabi-sabi, finding beauty in imperfection, impermanence, and incompleteness. A cracked tea bowl isn't ruined, it's enriched by its history. A weathered wooden gate isn't failing. It's becoming more itself through interaction with time and elements. The cherry blossoms are most beautiful precisely because they fall so quickly. Wabi-sabi teaches that impermanence isn't something to fear or resist.
It's the fundamental truth of existence, and accepting it allows deeper appreciation of each moment. Three-Eye Atlas. Whether natural or artificial, embodies impermanence. It existed for billions of years in one form. It passed our sun and transformed into something different. Eventually, it will leave our solar system and continue transforming in ways we'll never witness.
We caught it in a single moment of that endless transformation. We saw it when it was briefly bright, briefly active, briefly observable. In a few months it will fade from our view forever. That brevity doesn't diminish the encounter. It enriches it. We were here at exactly the right moment. We had instruments pointed at exactly the right place. We received light from an object that has traveled farther and seen more than anything humanity has ever created. And we recognize that light as meaningful, as worth studying, as worthy of wonder. So perhaps Three-Eye Atlas didn't blow apart. Perhaps it distributed itself. Perhaps what looked like catastrophic failure was actually successful completion of a mission phase. Or perhaps it was just a comet, ice and rock and chemistry responding to solar heat in ways we don't fully understand yet breaking apart, because that's what happens when frozen volatiles warm up faster than structure can accommodate. Either way, what remains? Trajectories,
Orbits. Paths through space that are now established that will persist for millions of years. If fragments exist, they're traveling toward destinations, maybe random, maybe predetermined, where they'll continue whatever journey they began eons ago. Data. Images, captured spectra, recorded orbital elements calculated, information gathered by human instruments that will be analyzed for decades, that will inform our understanding of interstellar objects for generations. Questions. The anomalies that made Three-Eye Atlas strange don't disappear just because the object might have fragmented. The nickel remains unexplained. The blue glow remains mysterious. The acceleration still doesn't match what natural processes alone should produce. And something else remains, the possibility that we're not alone. That fragmentation wasn't death, but distribution. That we're being observed by the scattered remnants of something that came here deliberately. The fragments, real or metaphorical, continue their journeys. Some toward Jupiter, some toward the Kuiper Belt, some perhaps curving back toward inner planets. Each carrying a piece of the story, each a word in a sentence we're still learning to read. And we remain watching, waiting, wondering what those fragments might become, what they might do, whether they'll reveal themselves or remain hidden among the countless natural objects that populate our solar system. Scattering is not ending. Scattering is continuation by other means. Let's reimagine what happened at perihelion. The narrative we've been carrying that Three-Eye Atlas might have exploded or blown apart contains an assumption about destruction that might be entirely wrong. What if what we witnessed wasn't death but birth? Not ending but beginning? Not a comet breaking under stress, but a comet releasing what it carried all along? Think about how life spreads on Earth. A dandelion doesn't die when it releases its seeds to the wind. It transforms. The flower that was singular becomes plural, hundreds of seed heads drifting on air currents, each carrying the potential for new growth. The parent plant isn't destroyed, it's distributed. Many trees produce seed pods that crack open violently, flinging seeds in all directions. The plant isn't killing itself, it's maximizing the geographic spread of its offspring. Ocean-dwelling creatures like jellyfish reproduce by fragmentation. A single jellyfish polyp can split into dozens of ephirae, each becoming an independent organism. The original polyp didn't die, it multiplied. What if Three-Eye Atlas works similarly? What if the breaking apart? We worried about the catastrophic mass loss calculations suggested the fragmentation that should have occurred. What if all of that was always part of the design? Not a failure, but a feature. Consider the engineering challenge of interstellar exploration. You want to study a solar system, multiple planets, diverse environments, various distances from the star. Sending one large probe to visit each planet sequentially would take decades, maybe centuries.
The mission would age, systems would degrade, and you'd gather data slowly. But if you sent one mothership that could deploy smaller probes at optimal moments, each specialized, each targeted to a specific destination, you could observe an entire solar system simultaneously. Parallel data collection, multiple vantage points, redundancy in case any individual probe fails. The deployment would ideally happen at perihelion when the sun's gravity provides maximum assist, when small velocity changes translate into large orbital differences. You'd time it precisely, release your payload, and let orbital mechanics do the work. From Earth watching this happen, what would we see? We'd see a single object approaching the sun. We'd see it brighten dramatically as it neared perihelion. We'd see it disappear behind the sun's glare. And when it emerged, we'd see, what a debris field, multiple smaller objects. Or perhaps the deployment would be subtle enough that we wouldn't see it at all with our current instruments. There's a philosophical principle here worth contemplating. In Buddhist thought, there's the concept of anatta, non-self, or the idea that what we perceive as singular entities are actually collections of components with no inherent unified identity. A person isn't a fixed self, but a constantly changing aggregation of cells, thoughts, experiences. In quantum physics, we talk about wave-particle duality, light behaving as both wave and particle, depending on how we observe it. The question, what is light, doesn't have a simple answer. It depends on context, on measurement, on the frame of reference. 3i Atlas might be teaching us something similar about identity and continuity. Was it ever really one object? Or was it always a collection of components traveling together, held by weak forces awaiting the right moment to diverge into independent trajectories? If it released probes at perihelion, did 3i Atlas die? Or did it simply become more honest about what it always was? Many things traveling together for a while, then separating to pursue different destinies. Every shard of a broken comet carries information about the whole. When scientists study meteorites, fragments of asteroids that have fallen to Earth, they're analyzing pieces of objects that broke apart long ago. Each meteorite tells a story about formation conditions, about the chemistry of the early solar system, about processes that shaped our cosmic neighborhood billions of years ago. The fragments are as valuable as the intact object would have been, sometimes more so because breaking apart exposes internal structure that was hidden when everything was whole. If 3i Atlas fragmented, each piece carries a record. The chemical composition, the isotopic ratios, the structural properties, all preserved, all available for study if we can observe closely enough. But there's another kind of information that fragments carry intention. If you were designing a probe to study our solar system and you wanted to maximize your data collection, you wouldn't keep everything together. You'd fragment deliberately. Each piece would have a mission. Each piece would be a message in itself, carrying instruments, carrying samples, carrying whatever you wanted delivered to specific locations. The fragments wouldn't be debris, they'd be emissaries. Let's think about this from an information theory perspective. Claude Shannon, working at Bell Labs in 1948, founded information theory by asking a simple question: how do you transmit messages reliably through noisy channels? His answer revolutionized communication redundancy. You encode the message multiple times, send it through multiple channels, use error correction codes that allow reconstruction even if parts are lost. The Mars rovers use this principle. Curiosity and Perseverance don't send data once. They send it multiple times through multiple antennas at multiple times of day. NASA wants to ensure that important discoveries aren't lost because a single transmission failed. If you're sending information across interstellar distances, across millions or billions of years, Shannon's principles apply even more urgently. You can't risk a single point of failure. You can't put all your data, all your samples, all your instruments in one fragile package. You fragment, you distribute, you ensure that even if 90% of your mission fails, the remaining 10% can complete essential objectives. From Earth watching this strategy unfold, fragmentation looks like catastrophic failure. But from a systems engineering perspective, it's resilience.
It's redundancy. It's the best way to ensure mission success across timescales where accidents and failures are inevitable. Consider the biological parallel spores. Fungi reproduce by releasing millions of tiny spores into the air. Each spore is a potential new fungus, carrying the complete genetic information needed to start a colony. Most spores fail, they land in hostile environments, dry out, get eaten, never germinate. But the strategy works because even a tiny success rate multiplied by millions of attempts results in propagation. The mushroom doesn't break apart in failure when it releases spores. It achieves its evolutionary purpose. The visible fruiting body, the part we call a mushroom, is just the reproductive structure. The main organism is the mycelial network underground, which persists whether the mushroom succeeds or fails. If 3i Atlas is artificial, maybe the large visible object is like the mushroom, the delivery system, the fruiting body, the part designed to be seen. And the actual organism, the mission, the data collection network, the intelligence, is what gets released, what becomes distributed, what persists even after the parent body is gone or departed. We're watching the mushroom and asking, is it dying? When we should be asking, what is it releasing? And where are those spores going? There's also a principle from distributed computing, Byzantine fault tolerance. In networked systems where some nodes might fail or even behave maliciously, you design systems where consensus can still be reached, where the network continues functioning even if a significant percentage of nodes are compromised. You do this through redundancy, through voting mechanisms, through multiple pathways for information flow. An interstellar mission faces similar challenges. You can't predict what will fail. You can't know which instruments will survive, which will malfunction, which will encounter environments they weren't designed for. So you build redundancy into the architecture itself. Multiple probes, each semi-autonomous, each capable of basic functions, each carrying copies of critical information. If one fails, the others continue. If communication between them is lost, each can still complete its mission independently. The system degrades gracefully rather than failing catastrophically. This is sophisticated engineering. This is how you build systems meant to last millions of years, to cross distances where real-time control is impossible to operate in environments you can't fully predict. And from our perspective, watching such a system deploy, it would look like a comet breaking apart at perihelion, multiple objects scattering on different trajectories, each piece going its own way, apparently independent, apparently uncontrolled. Unless they're not uncontrolled. Unless each piece knows exactly where it's going. Now consider what each fragment might carry if this scenario is even partially correct. Scientific instruments, obviously. Spectrometers to analyze planetary atmospheres, cameras to image surfaces, particle detectors to measure solar wind and cosmic rays, seismometers to study internal structure if any fragment impacts a body, magnetometers to map magnetic fields, each probe specialized for different observations together, providing comprehensive data about the entire solar system, but maybe more than instruments, maybe samples. If 3i Atlas traveled for billions of years, it passed through regions of interstellar space we'll never reach. It might carry dust from other stellar systems' ice that formed in molecular clouds with different chemistry than ours, maybe even biological material if life exists elsewhere and survives in frozen form. If fragments impact planets or moons in our solar system, they deposit those samples. Contamination from our perspective, panspermia from theirs. A way of sharing genetic or chemical information between stellar systems, using comets as seed pods, using gravity to deliver payloads to interesting locations. Or maybe information in more direct forms.
Memory storage if they have technology for long-term data preservation. Cultural artifacts if they want to communicate who they are. Mathematical or scientific constants encoded in physical structures like the hydrogen line frequency they might have used for the wow signal but written in matter rather than radio waves. Each fragment becomes a library, a museum, a message in a bottle cast across the cosmic ocean. The ancient Library of Alexandria was destroyed by fire. All that knowledge, geometry from Euclid astronomy, from Hipparchus poetry, from Sappho medical texts, from Herophilos, much of it lost forever because it existed in only one place. Civilizations since have learned. We distribute knowledge now. Multiple copies in multiple locations. The internet is redundant by design. Important cultural artifacts are digitized and stored in multiple archives. The Svalbard Global Seed Vault in Norway preserves seeds from around the world in case of agricultural catastrophe. If you're a civilization capable of interstellar travel, you've learned this lesson too. You don't put all your knowledge, all your cultural heritage, all your scientific achievements in one place. You send it out, you fragment it, you ensure that even if your homeworld is destroyed, even if your civilization ends, something survives. Someone might find it, someone might learn from it, someone might remember you. Maybe that's what 3i Atlas is, a fragment of someone else's Svalbard vault, a piece of someone else's distributed archive. Not a probe studying us, but a library seeding itself across the galaxy, hoping that somewhere, someday, someone will read what it carries. And we're here right now at the exact moment when that library passes through our system, when we're advanced enough to notice it, but still innocent enough to wonder what it is. Whether any of this is true or all of it is fantasy, the principle remains: fragmentation is not always failure. Sometimes it's strategy. Sometimes it's success. Sometimes it's the only way to ensure that anything survives the journey. 3i Atlas came from distance beyond measure, glowed briefly in our sky, and may have scattered itself across our solar system in ways we won't detect for years or decades. And if it did, each fragment carries a piece of the story. Each shard remembers the whole. Each messenger, if that's what they are, knows its mission. We just have to find them. We just have to learn how to read what they carry. And maybe, just maybe somewhere in those fragments is an answer to the question we've been asking since we first looked up at stars. Are we alone? Here's a lesson from ecology. Scattering is resilience. Species that concentrate in one location are vulnerable. One disaster, disease, drought, predation can destroy the entire population, but species that scatter, that spread across diverse habitats, survive. The loss of one group doesn't mean extinction. Others persist, adapt, eventually repopulate. This strategy works in information systems too. Distributed networks are more robust than centralized ones. If you want data to survive, you don't put it all in one place. You fragment it, replicate it, distribute it across multiple nodes. If 3i Atlas was carrying anything, data instruments, biological samples, cultural artifacts from whatever civilization might have sent it, fragmenting at perihelion would ensure survival. Even if one piece is destroyed or lost, others continue. The mission persists through its distributed components. From our perspective, this looks like breaking apart. From a systems design perspective, it looks like redundancy, like wisdom, like something that understands how to endure across cosmic timescales. Let's bring this back to human experience because we understand renewal in our own lives. Every 7 years, most of the cells in your body are replaced. The atoms that made up you in childhood are no longer present. You're materially a different person, reconstructed gradually from food, water, air. Yet you maintain continuity. You're still you, same memories, same identity, same sense of self, despite being physically different matter. Or consider relationships. Friendships that were close become distant. People we love drift away. But new connections form, new intimacies develop. The community that surrounds us is always changing. always being rebuilt, fragments departing and new elements arriving. This is the human experience of being a broken comet. We're constantly fragmenting and reforming, losing pieces of ourselves and gaining new ones, maintaining identity through change rather than through stasis. When we see 3i Atlas potentially breaking apart, maybe we're seeing our own reflection. Maybe we recognize in its fragmentation the same process of transformation that governs our own lives. And if we can find meaning and continuity in our own constant renewal, perhaps we can extend that understanding to an ancient traveler doing the same thing on a cosmic scale. There's a Japanese aesthetic principle called wabi-sabi, finding beauty in imperfection, impermanence, and incompleteness. A cracked tea bowl isn't ruined, it's enriched by its history. A weathered wooden gate isn't failing, it's becoming more itself through interaction with time and elements. The cherry blossoms are most beautiful precisely because they fall so quickly.
Wabi-sabi teaches that impermanence isn't something to fear or resist. It's the fundamental truth of existence, and accepting it allows deeper appreciation of each moment. 3i Atlas, whether natural or artificial, embodies impermanence. It existed for billions of years in one form. It passed our sun and transformed into something different. Eventually, it will leave our solar system and continue transforming in ways we'll never witness. We caught it in a single moment of that endless transformation. We saw it when it was briefly bright, briefly active, briefly observable. In a few months, it will fade from our view forever. That brevity doesn't diminish the encounter. It enriches it. We were here at exactly the right moment. We had instruments pointed at exactly the right place. We received light from an object that has traveled farther and seen more than anything humanity has ever created. And we recognize that light as meaningful, as worth studying, as worthy of wonder.
So perhaps 3i Atlas didn't blow apart. Perhaps it distributed itself. Perhaps what looked like catastrophic failure was actually successful completion of a mission phase. Or perhaps it was just a comet, ice and rock and chemistry responding to solar heat in ways we don't fully understand, yet breaking apart, because that's what happens when frozen volatiles warm up faster than structure can accommodate. Either way, what remains? Trajectories, orbits, paths through space that are now established that will persist for millions of years. If fragments exist, they're traveling toward destinations, maybe random, maybe predetermined, where they'll continue whatever journey they began eons ago. Data, images captured, spectra recorded, orbital elements calculated, information gathered by human instruments that will be analyzed for decades, that will inform our understanding of interstellar objects for generations. Questions. The anomalies that made 3i Atlas strange don't disappear just because the object might have fragmented. The nickel remains unexplained. The blue glow remains mysterious. The acceleration still doesn't match what natural processes alone should produce. And something else remains, the possibility that we're not alone. That fragmentation wasn't death, but distribution. That we're being observed by the scattered remnants of something that came here deliberately. The fragments, real or metaphorical, continue their journeys, some toward Jupiter, some toward the Kuiper Belt, some perhaps curving back toward inner planets, each carrying a piece of the story, each a word in a sentence we're still learning to read. And we remain watching, waiting, wondering what those fragments might become, what they might do, whether they'll reveal themselves or remain hidden among the countless natural objects that populate our solar system. Scattering is not ending. Scattering is continuation by other means. Every night somewhere on Earth, someone tilts their head back and looks at stars. It's an ancient gesture. Homo sapiens has been doing it for 300,000 years. Before that, earlier hominids looked up too. Before them, mammals, reptiles. The first fish that crawled onto land, all oriented to the sky, tracking sun and moon, navigating by celestial markers. Looking up is more than curiosity. It's a form of prayer. An acknowledgement of something larger than ourselves. a reaching toward mystery, a recognition that we exist within vastness we didn't create and don't control. When people around the world watch for 3i Atlas, when they read updates, share articles, check for new images, they're participating in this ancient ritual. They're looking up collectively, asking the same question our ancestors asked around fires. What is that light? What does it mean? Light pollution has stolen the night sky from billions of people. In cities, you can barely see stars. The Milky Way, that river of light that inspired myths in every culture, is invisible to most humans alive today. But people still look up, still search for connection with something beyond the immediate, the terrestrial, the human scale. 3i Atlas provided that connection. For a few months, professional astronomers and amateur stargazers shared the same target. The same object drew the attention of PhD astrophysicists and curious teenagers with backyard telescopes. News articles reach people who never think about astronomy. Social media brought the mystery to audiences that usually ignore space science. For a moment, we were all looking at the same thing, all asking the same questions, all participating in the same act of wonder. That participation is a form of prayer, regardless of whether anyone involved is religious. Prayer at its core isn't about asking for intervention. It's about acknowledging something beyond the self.
It's about joining consciousness with something larger, a community, a tradition, a universe that predates and will outlast individual existence. There's a Jewish tradition called Havdalah, marking the end of Sabbath and the beginning of the new week. Part of the ceremony involves lighting a braided candle, multiple wicks woven together, creating a flame brighter than any single wick could produce. The symbolism is beautiful individual lights combining into something greater than their sum, many flames becoming one fire. Every person who watched 3i Atlas, who read about it, who wondered what it might be, each one added light to a collective flame of attention. Individually, we're small. Our observations are limited. Our understanding is partial. But together, pooling attention-sharing data, building on each other's insights, we create something powerful. The professional observations were crucial. Hubble Webb ground-based telescopes with advanced instruments. But the amateur observations mattered too. Citizen scientists processing punch satellite images, finding patterns that automated systems missed. Enthusiasts maintaining tracking websites, making information accessible. People sharing articles, sparking discussions, keeping the story alive in public consciousness. Each contribution is a candle lit for the unknown. Each view, each comment, each moment of genuine curiosity adds to the collective illumination. Let's return to August 15, 1977, and the WOW signal, that 72-second burst of radio energy at the hydrogen line detected once and never repeated. Avi Loeb calculated that 3i Atlas came from the same region of sky within 9 degrees. The probability 0.6%, low enough to be noteworthy, high enough to be possibly coincidental. But here's what interests me more than the probability, the poetry of it. If the WOW signal was artificial, if it was someone saying hello, then our response was silence. We noticed, we noted it, we moved on. The telescope that heard it was demolished. And now, 48 years later, something arrives from that same direction. Moving at interstellar speeds, it would have left its home system around the time the WOW signal reached us. Maybe this is coincidence. Maybe it's not even correlation, just pattern-seeking brains finding meaning in randomness. Or maybe it's a message and a messenger. The signal, we're coming. The visitor, we're here. Let's examine the WOW signal more carefully because its details are extraordinary. The signal was detected at 1420.456 MHz, right at the hydrogen line, the frequency emitted when neutral hydrogen atoms flip their electron spin. This is not an arbitrary frequency. It's the most abundant spectral line in the entire universe, the frequency that radio astronomers everywhere use as a universal reference point. If you wanted to send a signal that would be recognized as artificial, this is the frequency you'd choose. The signal intensity was 30 times stronger than background noise.
For context, typical cosmic sources that Big Ear detected were maybe 2-3 times above background. This was unmistakable, obvious, impossible to miss, and it lasted exactly 72 seconds, exactly the length of time Big Ear's fixed antenna could observe any particular point in the sky, as Earth's rotation carried the telescope's field of view across the heavens. Think about that timing. If the signal had been continuous, Big Ear would have detected it rising in intensity as the source entered the beam, peaking when aligned, then falling as it exited. Instead, the signal appeared at near maximum intensity, stayed strong, then cut off precisely when Big Ear's observation window closed. Either the source knew Big Ear's scanning pattern and timed the transmission accordingly, or the signal itself was exactly 72 seconds long and we happened to catch it at the exact moment it was transmitted, a coincidence so unlikely it strains belief. Jerry Emin, the astronomer who discovered the signal in the computer printout, wrote later that he immediately recognized it as the most interesting thing he'd ever seen in the data. Not because he jumped to conclusions about aliens, but because nothing natural produces that pattern, that frequency, that intensity, that duration. The follow-up observations found nothing. Big Ear looked at that same patch of sky dozens of times over the following months and years. Nothing. Other telescopes have since searched that region at various frequencies. Silence. Whatever produced the wow signal either moved, stopped transmitting, or was a genuinely one-time event. Now consider 3i Atlas. In 1977, it was approximately 600 astronomical units from Earth, about 15 times farther than Pluto, deep in the outer solar system, or just beyond. If it transmitted the wow signal from that distance, the timing is precise. 3 days for light and radio waves travel at light speed to cross the distance. The signal was detected August 15th. If it came from 3i Atlas, it was transmitted August 12th. What happened on August 12th that might cause a spacecraft to transmit activation sequence system check, announcement of arrival in a new stellar system? Or, and this is pure speculation and maybe, August 12, 1977 was when 3i Atlas first detected our radio emissions. Earth has been broadcasting radio waves into space since the early 20th century. Those waves expand outward at light speed, creating an ever-growing bubble of radio noise centered on our sun. In 1977, that bubble had a radius of about 70-80 light-years. If 3i Atlas was 600 AU away in August 1977, and if it had been traveling at its current speed of 68 kilometers, then working backward, it would have been within 80 light-years of Earth sometime in the early 20th century, right when our radio bubble was forming. This is speculation stacked on speculation, but here's the scenario. An interstellar probe traveling through the galaxy detects radio emissions from a previously silent star system. This is noteworthy. Technological civilizations are presumably rare. The probe adjusts course to investigate. As it approaches the outer edges of the system, it sends a test signal. "We detected your transmissions. We are approaching. This is what we sound like." And we responded with, "Wow," on a printout, and then demolished the telescope to build a golf course. If this is even remotely close to what happened, the irony is devastating. We spent decades broadcasting signals saying, "We're here, is anyone out there?" Someone responded, and we missed it. But whether this connection is real or imagined, it serves a purpose. It reminds us that the universe might be listening, that the signals we send radio waves carrying our television shows our music. Our attempts at deliberate communication might not disappear into empty void. They might reach someone, something might respond, and that possibility, however slim, however speculative, changes how we see ourselves. We're not just observers of the cosmos, we're participants in it, potential conversants in a dialogue that spans light years and millennia. The wow signal, whether natural or artificial, is part of our mythology now, part of how we tell stories about our place in the universe. It's a modern campfire tale, a mystery that connects us to wonder, a reminder that we don't yet know everything. It's the message that might have been a message, the contact that might have been contact forever, ambiguous, forever, compelling. And 3i Atlas arriving from that same direction 48 years later becomes part of the same story. Maybe not literally, maybe there's no causal connection, but narratively, mythologically, they're linked. They're chapters in the same book, the book of things that make us look up and wonder. In 50 years, when other interstellar objects have passed through our system, when we have more data points, more context, more understanding, people will look back at 2025 and the mystery of 3i Atlas. They'll connect it to the wow signal, whether the connection is real or not. They'll weave it into humanity's story of learning to see ourselves as part of a cosmic community, and maybe that's enough. Maybe the truth of the connection matters less than what it teaches us about hope, about curiosity, about remaining open to the possibility that we're not alone. During the weeks when 3i Atlas was most active, something remarkable happened online. Scientists shared data in real time. Amateur astronomers posted observations. People with no technical background read articles, watched videos, discussed possibilities. The conversation crossed disciplines: astronomy, physics, chemistry, philosophy, even theology. Comment sections became forums for genuine inquiry. Redditors compiled information into detailed threads. YouTube exploded with content, some rigorous, some speculative, all driven by curiosity. This is what I mean by cosmic prayer. Not literal prayer to or about 3i Atlas, but the communal act of directing attention toward mystery, of gathering around something that none of us fully understand, of sharing the experience of not knowing together. Churches and temples provide this function for religious communities, spaces where people gather to contemplate what's beyond comprehension, to acknowledge their smallness in the face of vastness, to find comfort in shared uncertainty. For those without traditional religious practice, 3i Atlas offered something similar: a focal point, a shared mystery, a reason to come together around questions that don't have easy answers. Everyone watching 3i Atlas, regardless of their conclusions about what it is, shares something fundamental: the recognition that we're part of something larger. The skeptics insisting it's natural still feel awe at a comet billions of years old passing through our cosmic neighborhood. They're connecting with deep time, with distances that dwarf human experience, with natural processes that operate at scales we can barely fathom. The believers hoping it's artificial field connection, of a different sort connection to potential intelligence, to the possibility that consciousness exists beyond Earth, to the idea that someone out there might be looking up at their own sky, asking the same questions we ask. Both groups are participating in the same act, trying to understand our relationship with the universe, trying to locate ourselves in the vast map of space and time, trying to answer the question that defines human consciousness. What does it mean that I exist here now, aware of infinity? That question is a prayer, whether framed in religious language or not. It's the most profound prayer humans can offer. Help me understand my place in this. Medieval monks used to practice something called lectio divina, divine reading. They would read sacred texts slowly, repeatedly, looking for layers of meaning, literal, allegorical, moral, mystical. The practice wasn't about extracting information, it was about transformation through contemplation. Studying 3i Atlas can function similarly, the literal level. It's an interstellar object passing through our solar system with unusual properties. The allegorical level. It represents the unknown, the stranger at the door, the message from afar. The moral level. It teaches us about how we respond to mystery, with curiosity or fear, with openness or defensiveness, with humility or arrogance. The mystical level. It invites us into relationship with vastness, with time that exceeds our lifespan, with distances that dwarf our world. Each level is valid. Each offers something valuable. You don't have to believe. Three-Eye Atlas is artificial to experience its mystical dimension, the way it makes you feel small and connected simultaneously, the way it opens questions about existence that can't be answered with science alone. This is the astronomy of the soul, using celestial phenomena not just to understand physics, but to understand ourselves, to locate our inner experience within the outer cosmos, to find metaphors in stars that help us navigate the darkness within. Here's what I think the cosmic prayer actually is. We are here. We are looking. We are trying to understand. If anyone else is out there doing the same thing, we see you. Or we're trying to. We haven't given up. We're still watching the sky, still asking questions, still hoping that we're not alone in this vast darkness. Every telescope pointed at Three-Eye Atlas is saying this. Every paper analyzing its composition, every simulation modeling its trajectory, every discussion debating its nature, all of it is this prayer in different forms. We're announcing ourselves through our curiosity. We're saying this is what consciousness does. It reaches toward what it doesn't understand. It builds instruments to see farther. It stays up late wondering what that light might be. And maybe, just maybe, something out there recognizes that behavior, sees in our astronomical investigations the same drive they felt when they were where we are now, remembers when they were the young species just beginning to look beyond their own world, just starting to ask if anyone else was out there. If Three-Eye Atlas is artificial, if it's gathering data about us, this is what it would see: a species that noticed it, that tracked it, that tried to understand it. A species that built temples to curiosity called observatories. A species that, despite all our divisions and conflicts, can still gather around shared wonder. That's not a bad message to send, not a bad way to be seen. And if Three-Eye Atlas is natural, just ice and rock and chemistry, then our prayer is still heard. Not by intelligence, but by the universe itself. The cosmos doesn't answer in words, but it answers in phenomena. It gives us supernovae and pulsars, black holes, and galaxies, interstellar visitors that arrive precisely when we're advanced enough to detect them but still humble enough to be awed by them. The prayer and its answer are the same act. We look up, the universe looks back. In that mutual gaze, something sacred happens, not religious necessarily, but profound. A recognition that existence is strange and beautiful, and worth contemplating, worth celebrating, worth the effort of trying to understand. December 19th will come and go. Three-Eye Atlas will make its closest approach to Earth, still 168 million miles away. Too far to see clearly, close only in astronomical terms. Telescopes will observe. Data will be collected. Some questions will be answered, others will remain, and then it will recede. Back into the darkness between stars, moving away from our sun, cooling. Dimming, becoming once again the frozen traveler. It was for billions of years before it briefly warmed in our light. By March 2026, it will pass Jupiter's orbit. By the end of 2026, it will be beyond Saturn. Within a few years, it will be farther from the sun than Neptune, entering the outer reaches where sunlight becomes indistinguishable from starlight. Eventually, Three-Eye Atlas will leave the sun's gravitational influence, entirely returning to true interstellar space. The voyage that brought it here, millions or billions of years long, will continue. Maybe toward another star system. Maybe toward nothing in particular, just the endless drift through the galaxy's spiral arms. We'll never see it again, never get another chance to study it up close. This encounter is singular, unrepeatable, a moment in cosmic time that opened and will close. So what remains when the object itself is gone? First data, gigabytes of observations, images from dozens of telescopes, spectra showing chemical compositions, orbital measurements tracking every meter of its trajectory. This data will be analyzed for decades. Students not yet born will write dissertations on Three-Eye Atlas. Researchers will return to these observations whenever a new interstellar visitor arrives, comparing contrasting building theories. Second questions. The anomalies don't disappear when 3i Atlas does. Why was the nickel emission so strong? What caused the blue glow at perihelion? How did it maintain structural integrity under accelerations that should have fragmented it? These questions persist, demanding answers, driving future research. Third precedent. 3i Atlas is the third confirmed interstellar object, but it's the first we discovered early enough to watch through its entire passage. The first we studied with instruments like Webb and the latest generation of ground-based telescopes. Everything we learned informs how we'll observe the next visitor and the next, because there will be others. The universe is full of wanderers. Now that we know what to look for, we'll find more. Some will be boring exactly what models predict. Others might be even stranger than 3i Atlas, but beyond the scientific legacy, there's something more personal that remains. Everyone who followed this story, who wondered about this mysterious traveler, who stayed up reading about 9 anomalies and probability calculations, you're changed by it. Subtly, maybe imperceptibly, but changed. Because once you've contemplated the possibility that we're not alone, that intelligence might exist beyond Earth, that something might have come here deliberately, you can't fully unthink it. The door once opened doesn't close completely. You'll look at future astronomical discoveries differently. When the next interstellar object arrives, you'll remember 3i Atlas. You'll compare. You'll wonder. You'll be more attuned to the possibility of the extraordinary hiding in what first appears ordinary. And more broadly, you've experienced what it means to sit with genuine cosmic mystery, to follow a story as it unfolds in real time, not knowing how it ends, not having access to easy answers. To hold multiple contradictory possibilities in your mind, simultaneously natural and artificial comet and spacecraft, without collapsing prematurely into certainty. That's a skill. That's a way of being with uncertainty that's increasingly rare in a world that demands immediate clarity, that treats ambiguity as failure rather than as the normal state of frontier knowledge. Here's something beautiful about how we see distant objects. When you look at a star, you're seeing light that left that star years or centuries ago. The star as it was then, not as it is now. You're looking at history. You're seeing across time. 3i Atlas is billions of years old. When we observe it, we're seeing matter that formed when the universe was young, when our solar system didn't exist yet, when the atoms that would eventually become Earth and life and humans were still scattered across different regions of the galaxy. The light we see from 3i Atlas isn't just reflected sunlight. It's an echo of deep time, a message from eons past, a physical presence of ancient history in our contemporary sky. But here's the deeper truth. The light we see isn't just from 3i Atlas. It's from us too. We shine light at it, radar signals, for instance, trying to measure size and rotation. We illuminate it with our attention, our instruments, our curiosity. And that illumination changes what we see. Not physically, we're not altering the object itself, but perceptually. The meaning we extract from observation depends on what we bring to the act of observing. Two people looking at the same data can see different things, not because the data is different, but because they're asking different questions, carrying different frameworks, hoping for different answers. The light that remains after 3i Atlas is gone isn't just electromagnetic radiation preserved in digital files. It's the light of consciousness encountering mystery. The light of minds reaching towards something they don't understand. The light we generate when we refuse to accept easy explanations and keep asking, but what if? There's a principle in quantum mechanics called the observer effect. The act of observation changes what's being observed. Measuring a particle's position affects its momentum. Observing which slit a photon passes through eliminates the interference pattern. The observer and observed are entangled, inseparable, mutually constitutive. This isn't mysticism, it's physics. At quantum scales, there's no such thing as passive observation. Every measurement is an interaction. Every observation is a collaboration between observer and observed. At cosmic scales, we assume observation is passive. Light reaches our telescopes, we record it, we analyze it, and we believe we're seeing the object as it really is. But that's not quite true either. The filters we use determine which wavelengths we see. The exposure times determine what brightness levels we capture. The processing algorithms determine how we enhance or suppress features in images. Every choice we make about how to observe shapes what we observe. And beyond the technical choices, there are conceptual ones. What questions we ask determine what patterns we notice. If you're looking for evidence of natural processes, you'll emphasize data that fits those models. If you're looking for evidence of artificiality, you'll emphasize anomalies. Same light, different interpretations based not on deception, but on the fundamental fact that observation requires framework. The medieval Islamic scholar Ibn al-Haytham, sometimes called al-Hazan, was the first to truly understand light. He rejected the Greek idea that eyes emit light rays. He recognized that light reflects off objects and enters the eye. He invented the camera obscura. He understood refraction demonstrated that light travels in straight lines, founded what we now call optics. But he also understood something deeper, that seeing is not passive reception, but active interpretation. The eye receives light, but the mind constructs vision. What we see is always already interpreted, filtered through expectation and experience. This insight from 11th century Persia remains profound. We don't see reality directly. We see our brain's best hypothesis about reality, constructed from sensory data but shaped by everything we know, everything we expect, everything we hope or fear. When we look at 3i Atlas, what we see is partially the object itself. Photons carrying information about its chemistry, its temperature, its motion. But it's also partially us, our instruments, our theories, our debates, our cultural moment, our collective hunger for either confirmation or mystery, depending on what comforts us more. The light from 3i Atlas reaches us, but the meaning of that light is something we create. And that creation is not arbitrary, it's constrained by reality, by what the photons actually carry. But within those constraints, there's room for interpretation, for emphasis, for narrative. This is why the same data can support multiple hypotheses. This is why smart people examining the same observations can reach different conclusions. Not because anyone is lying or incompetent, but because observation at the frontier of knowledge is inherently underdetermined. The data doesn't force one interpretation. It allows several. And which one you favor depends on what you brought to the observation in the first place. So when we say, the light that remains, we're talking about something compound. The electromagnetic radiation captured in our archives, yes, but also the human response to that radiation. The questions it provoked, the wonder it inspired, the debates it sparked, the late nights spent analyzing spectra, the conferences organized to discuss findings, the public fascination that briefly made astronomy front-page news. All of that is light, too. Light in the broader sense, illumination, understanding the glow of consciousness, recognizing something worthy of attention. 3i Atlas brought light to us in the form of photons. We brought light to it in the form of attention. And in the interaction between those two kinds of light, something new emerged: knowledge, yes, but also uncertainty. Answers, yes, but also better questions. Conclusions, yes, but also deepened mystery, that emergent light. The third thing created, when consciousness meets cosmos, that's what remains. After 3i Atlas has moved beyond observability, that's the inheritance this encounter leaves us. Not just data about one interstellar visitor, but practice in how to hold mystery, how to remain curious without needing certainty, how to observe without collapsing possibility too quickly into conclusion. In Plato's allegory of the cave, prisoners watch shadows on a wall, mistaking them for reality. When one escapes and sees actual objects casting the shadows, then finally the sun itself illuminating everything, he undergoes transformation. He learns that what he thought was direct perception was actually mediated indirect, a representation rather than the thing itself. We're still in the cave. Our telescopes show us shadows light that has reflected or refracted or redshifted on its way to us. We never see cosmic objects directly. We see information that has traveled, transformed, been filtered by dust and distance and the limitations of our instruments. But unlike Plato's prisoners, we know we're seeing shadows. We've built elaborate techniques for inferring the reality that casts them. We've gotten very good at reading the shadows, at extracting maximum information from minimal light. 3i Atlas is a shadow on our wall, a pattern of photons that tells us something about an object we can't touch, can't directly sample, can't examine, except through the information that reaches us across millions of miles. And we've interpreted that shadow. We've argued about what shape must have cast it, what motion must have created it, what nature or artifice must have produced it. The shadow remains in our data archives, but the interpretation, the light we brought to understanding the shadow that remains in us, in how we think about interstellar objects now, in how we approach the next one, in how we've practiced the craft of inference, of sitting with ambiguity, of building hypotheses on incomplete information. Let me offer one final speculative thought. Maybe the significance of 3i Atlas has nothing to do with whether it's natural or artificial. Maybe what matters is how it functioned as a mirror, reflecting back to us our own capacity for wonder, our resilience in the face of uncertainty, our ability to collaborate across borders and disciplines in pursuit of understanding. Avi Loeb and his critics, despite their disagreement, are both motivated by the same thing: love of truth, desire to understand reality accurately, commitment to following evidence wherever it leads. The amateur astronomers and professional scientists, despite different levels of training and access to equipment, share the same curiosity, the same excitement about mystery. The general public reading articles and watching videos participates in the same human tradition that built Stonehenge and charted constellations and launched Voyager toward interstellar space, the tradition of looking up and asking, what is that 3i Atlas, whatever it is, catalyzed all of this? It brought together people who rarely interact. It created conversations across expertise levels. It made astronomy front-page news for a while, brought cosmic mystery into cultural consciousness. If it's a natural comet, it still accomplished something remarkable. It reminded us why we explore, why we build telescopes, why we stay up late wondering about lights in the sky. And if it's artificial, if it's gathering data about our civilization, then what it's recording is this: humans noticed, it tracked, it tried to understand it, and in the process remembered what's best about our species. Curiosity, collaboration, the refusal to stop asking questions, even when answers don't come easily. The people listening to this documentary right now, many of you are lying in darkness, headphones in, using these words and this story to transition from waking consciousness into sleep. There's something appropriate about that. Something right about contemplating cosmic mysteries as you drift toward unconsciousness. Because sleep is where we process, where our minds integrate information, consolidate memories, make connections that elude us during waking hours. The questions raised by 3i Atlas. What is it? Why is it here? Are we alone? These aren't questions that solve themselves through pure logic and data analysis. They're questions that require dreaming, require imagination, require the part of consciousness that can hold paradox without demanding resolution. As you fall asleep tonight, carrying thoughts of an ancient traveler glowing blue in the sun's corona, accelerating through space for reasons we don't fully understand, let those thoughts settle into whatever part of your mind handles mysteries. Maybe tomorrow or next week or next year, some insight will surface, some connection you didn't see before, some way of holding the question that makes it less terrifying and more wondrous. or maybe not. Maybe Three-Eye Atlas will remain mysterious. Maybe we'll never know for certain what it was, what it carried, what it meant. And that's okay too. There's a practice in dream interpretation, not the fortune-telling kind, but the psychological kind pioneered by researchers like Calvin Hall and Eugene Aserinsky, that focuses on how dreams process unresolved tensions from waking life. Dreams don't solve problems so much as they explore them from different angles, trying out scenarios, testing possibilities without the constraints of logic or consequence. When you dream about Three-Eye Atlas tonight, if you do, your unconscious mind might play with the possibilities in ways your waking mind cannot. Maybe in your dreams, the comet becomes a ship and you meet its crew. Maybe it becomes a message written in light and you finally understand what it says. Maybe it becomes a mirror and you see yourself reflected in its ice and nickel. These dreams won't be scientifically accurate. They won't solve the mystery. But they might do something more important. They might integrate the experience of mystery into your deeper self, into the layers of consciousness that operate on metaphor and emotion rather than data and logic. Because here's a truth about human psychology. We need mysteries. Not unsolvable problems that frustrate us, but genuine unknowns that invite us to wonder. The human mind evolved to be curious, to seek patterns, to ask, what is that when confronted with the novel or strange? In our modern world, we've eliminated most everyday mystery. Wikipedia answers questions instantly. GPS tells us exactly where we are. Weather forecasts predict tomorrow's conditions. We've mapped the Earth, cataloged its species, explained its processes. This is progress. This is valuable. But it's also created a hunger for the genuinely unknown, for mysteries that can't be Google searched away, for experiences that still carry the frisson of not knowing. Three-Eye Atlas offers this. For a few months, it's been a real mystery, accessible to anyone with internet connection. You don't need advanced degrees to feel its strangeness. You don't need to understand orbital mechanics to wonder what the blue color means. You don't need to be a scientist to participate in the collective questioning. In ancient Greece, they understood the value of mystery. The Eleusinian mysteries were secret religious rites that participants underwent but could never speak about. Not because discussion was forbidden, but because the experience was ineffable beyond words, beyond explanation. Those who underwent the mysteries were transformed, but the transformation couldn't be communicated directly. It had to be experienced. Three-Eye Atlas is not religious, but it offers something similar, an experience of genuine cosmic mystery that transforms how you see the universe. Once you've contemplated the possibility that an interstellar visitor might be artificial, that something intelligent might have come here deliberately, you can't return to the naive certainty that we're alone. Once you've sat with 9 anomalies, each unlikely, together almost impossibly improbable, you can't dismiss the extraordinary so easily. Once you've practiced holding uncertainty, acknowledging that we genuinely don't know what Three-Eye Atlas is, you've developed a muscle that will serve you in all areas of life where certainty is unavailable but action is still required. This is the gift of cosmic mystery. It teaches us how to be comfortable with not knowing, how to remain curious without becoming paralyzed, how to take ambiguity seriously without collapsing into either skeptical dismissal or credulous belief. There's a Japanese concept called ma, the space between things, the pause between notes, the interval between breaths.
In traditional Japanese arts, music, flower, arranging architecture, ma is not empty space, but rather intentional void, negative space that gives meaning to the positive. The mystery of Three-Eye Atlas is ma. It's the space between what we know and what we don't know, between data and interpretation, between possibility and conclusion. That space is not absence. It's presence of a different kind. It's the room where wonder lives, where curiosity grows, where imagination works. As you drift toward sleep, let yourself inhabit that space. Don't rush to fill it with answers. Don't force it to resolve into either definitely a natural or definitely artificial.
Let it remain, may productive void, generative uncertainty, the pause between notes that makes the music meaningful. In the morning, Three-Eye Atlas will still be out there, moving away from the sun, continuing its journey. The mystery will still be unresolved. The questions will still be open. And you'll wake having spent the night in the company of something ancient and strange, something that passed through our cosmic neighborhood and left us wondering. That wondering is not weakness. It's not intellectual failure. It's exactly what we should feel when confronted with the genuinely unknown. It's the appropriate response to mystery, not grasping for premature answers, but sitting with the question, letting it work on you, letting yourself be changed by the encounter. Dream well. Dream deeply. And when you dream of Three-Eye Atlas, remember that you're part of a story larger than any individual life, the story of a species learning to ask better questions, learning to look beyond its own world, learning to recognize that the universe might be stranger and more wondrous than we ever imagined. And maybe, just maybe, somewhere in your dreams tonight, Three-Eye Atlas will send you a message.
Not in radio waves or spectroscopic signatures, but in the language that dreams speak, the language of symbol and metaphor, of emotion and intuition, of truths that can't be proven but can be felt. Listen for it, not with your ears, but with whatever part of you knows how to hear the universe when it whispers. Here's my final thought before we end this journey together. If Three-Eye Atlas is natural, just ice and rock and chemistry, it still remembers you in a way. The photons that bounced off its surface and reached your eyes, or your telescope or your computer screen showing images of it, carry information. Those photons interacted with Three-Eye Atlas, and now they've interacted with you. You're connected, however tenuously, by physics, by light. And if Three-Eye Atlas is artificial, if it's a probe gathering data about our solar system, about our planet, about our species, then you're recorded. Not individually, probably, but collectively. As part of humanity circa 2025, the species that noticed an interstellar visitor and tried to understand it. Either way, you're part of the story now. Your attention, your curiosity, your willingness to spend 2 hours contemplating cosmic mystery, that's data, that's signal, that's meaning. Three-Eye Atlas arrived from distance beyond comprehension, glowed briefly in our sky, and will depart toward distances we'll never cross. But in the few months we shared space with it, a connection was made. You looked up. It was there. Light traveled between you. And that light remains in memory and photographs in the changed way you see the universe, now that you've contemplated what strangeness it might contain. Sleep now. Dream of the distance. Dream of travelers older than mountains glowing blue against the sun. Dream of the questions we're still learning how to ask. And when you wake, the sky will still be there, still full of mysteries, still waiting for someone to look up and wonder. Somewhere between stars, Three-Eye Atlas continues its journey, maybe knowing we watched it, maybe carrying our image to places we'll never see, maybe not knowing or caring about us at all, but we know about it. We wondered, we tried to understand, we spent time, precious, finite human time, contemplating something ancient and possibly intelligent, possibly not definitely extraordinary. That contemplation is prayer. That wonder is worship. That curiosity is love in the purest sense, love of truth, love of mystery, love of the universe that contains both. The light remains, in data, in memory, in the changed way you see stars now, and somewhere something remembers you too.